Green's theorem is a very powerful statement that relates a path integral to a double integral. In this video, we're going to evaluate the path integral of this vector field over a path C directly, and then by using Green's theorem. The vector field x squared yi plus xy squared j, and then the path is a circle of radius 5 centered at the origin, moving counterclockwise around it, and that's important because Green's theorem is for counterclockwise oriented curves. Okay, so we're going to use Green's theorem. I'm using the tangential form of Green's theorem. First, we'll just evaluate this directly, and it's worth noting that if this was path independent, I should use the fundamental theorem of line integrals rather than do anything complicated to do it directly, or even using Green's theorem. This is a path in the plane, so if I think about my component test, I need to compare the partial of m and n, and it's only the one statement, which is really nice. And so I look at the partial with respect to y here, and I get minus x squared. And then the partial with respect to x here would be positive y squared, and those statements aren't equal everywhere. So this is not a conservative field. So I actually have to either compute it directly or use Green's theorem. I can't use the fundamental theorem of line integrals. All right, so we'll start by doing this computation directly. My vector field minus x squared y, xy squared, and my path is the circle of radius 5 centered at the origin. All right, well, my path integral is equal to this statement where I need to evaluate that vector field at my path and from 0 to 2 pi from a to b. So for us, we'll be going from 0 to 2 pi, and then we need to figure out what that integrand is going to be. So let's find f of r of t. Well, let's see, that's going to be a minus 25 cosine squared t times 5 sine t. And then I'll have 5 cosine t times 25 sine squared. So minus 125 cosine squared t sine t, comma 125 cosine t sine squared t. All right, we also need to know dr dt. And let's see, that's going to be minus 5 sine t, and then 5 cosine t. My integrand is the dot product of these two things. So let's see, that's going to be 625 cosine squared sine squared t plus 625 cosine squared t sine squared t, all dt. And I kind of ran out of room there. So let's see, thinking about that last statement, I have the same thing twice, so 625 and 625 is 1250 sine squared t cosine squared t dt. And that's what I'm integrating. Okay, well, let's see. I'm going to rewrite that. So I got the 1250, but I'm going to think of that as a sine t times cosine t squared. Well, and let's rewrite that. I'm thinking about a double angle formula for sine, so that'd be 1/2 of sine of 2t squared. So that's a quarter, so I have 1250 over 4, so 625 divided by 2 312.5 sine squared of 2t dt. All right, and now I can use a power reducing formula. Let's go on and write that 312.5 out front. And there's my power reducing formula for sine, and finally I just need to take an antiderivative. And I need to evaluate that from 0 to 2 pi. So I have 312.5 times pi minus 1/8 sine of 8 pi, well, that's going to be 0. Minus, well, 0. So I'm going to rewrite this as 625 over 2 pi. And so I've evaluated my path integral. Now I'm asked to do it again using Green's theorem. So hopefully we're going to get the same value we just did, 625 over 2 pi. But this time, instead of doing it directly, we're going to take a double integral over the region R. With respect to that area. So I need to take some partial derivatives. So the partial of n with respect to x, well, that's y squared. So I'm thinking about this double integral up here in blue being equal to y squared minus the partial of m with respect to y is a minus x squared over that region R. Well, what's my region R? Well, it's a circle of radius 5. And so now all of a sudden, I'm thinking, instead of thinking about this as a dy dx, that I want to think about this as a polar double integral. Because in polar coordinates, my circle's really easy to deal with. I'm integrating from 0 to 5 and from 0 to 2 pi. All right, so I have an r cubed in here to integrate. So that would be a 1/4 r to the 4th from 0 to 5. Still with a d theta there. And so I need to raise 5 to the 4th power. So I get 1/4, 5 to the 4th power, times, and I can go on and imagine integrating with respect to theta, and that would be a theta evaluated from 0 to 2 pi, so it would just be a 2 times pi. All right, well, 5 to the 4th is 625. The 4 and the 2 reduce, I get 625 pi over 2. And we get the same thing both times, and I think Green's theorem here gives me an easier way to approach this problem.